Partha is the first who wanted to intervene. Please, Partha.
Oh, thank you very much, Tim. That was a great talk. I want to stretch you a little bit on, it may be even mildly incoherent question, for which, forgive me if it is. You stressed rightly subsystems of the Earth system, which have bistability or multiple stability regimes, and you stressed attention on that. Mm-hmm. Now, these systems operate at different scales, spatial scales, as well as time. So I'm imagining now a parallel system on a spatial stage, or even with different elements, components, as it were, but operating, roughly speaking, at the same time scale. And then you have another set, which is on a different time scale, and you go up the order. Now, are there any, and these are nonlinear systems, all of them, and let's work with that thought, okay? And each of them has multiple stability states. But in the aggregate, are there some results, analytical results available, which suggest that if they're running in parallel, something like the law of large numbers is operating to keep the aggregate system looking fairly stable? But of course, it's hitting against other time scales, right? So if you look at the slice of, say, 500 million years, which is not a big deal by your kind of standards, your geological standard, it may look fairly stable, but then something hits. And is there some way of arranging one's thought? Are there mathematical results which allow you to have some kind of a thought? And in the greater scheme of things, we are concentrating on, I mean, we ended with looking at stability regimes in which we are wiped out. You just looked at it with multicellular objects. In the greater scheme of things, that may not amount to a big deal in the largest scale of things, maybe. But of course, it does for us. Are there any analytical results which we could appeal to have some sense of whether there's an averaging process? I have in mind, of course, the Gaia hypothesis, which is at the background, but that's a metaphor, whereas we have some analytical results here.
Yes, the short answer, there is some existing body of theory that pertains to this. Yep. I think I'd better take you into a longer conversation in the coffee break on the theory, the precise sort of dimensions and the contributors to that. I mean, one area we could talk about, slightly tangential, but is actually this whole notion of what is a mass extinction, because actually you expect a power law distribution of extinction sizes, and it would be somewhat arbitrary what you define as a mass extinction in that context. For what it's worth, the model I started with, our artificial biosphere, where all the catastrophes were internally generated, that produces a power law distribution of extinction sizes that fits the observed data pretty well. That doesn't mean it's the right model, but it slightly pertains to the question. I think you're asking something deeper about aggregate feedback dynamics. I think one of your questions was if you could have tipping at subscales, if you aggregate that over space or time, would it still potentially look like a smooth system? Well, it all depends on the scale then, but what we can say from the geologic record are we can pick up distinct instabilities or perturbation events, if you like, and we can also watch the recovery from those. They're relatively few and far between, but they're incredibly insightful. I didn't talk about one that was 55 or so million years ago at the boundary of the Paleocene and the Eocene epochs, the Paleocene-Eocene thermal maximum. People talk about it as a natural analog for the human fossil fuel burning, because we can see in our proxies for the long-term carbon cycle and temperature that the order of a few thousand billion tons of carbon were released to the atmosphere, and we see a persistent 5 degrees or more of global warming in a 100,000 year or more timescale for the ocean acidification and the carbon cycle and the temperature to recover. But so that's a global scale event with a negative feedback response with a particular timescale that actually fits our model of this silicate weathering feedback very well. That's still only a partial answer to your question, because you're asking a pretty deep question, which actually goes back to foundational work in cybernetics and systems theory. So maybe we'll do it over coffee, but characters like W. Ross Ashby, who was a British cybernetician in the 50s, actually made a machine, and he coined a concept of ultra-stability. He made a literal self-regulating machine, actually out of bomb navigation devices, 4 of them coupled together. He was actually interested at the time intellectually in questions around physiology and brain function and how we self-regulate. Without giving a long lecture on this, his metaphor was a cat putting its paw in a fire and withdrawing it, and how the cat's neurons might rewire so that it didn't make the same mistake again. But it's a beautiful piece of work, and actually if you understand the theory behind what Ashby wrote in the 50s, it's not a bad model for something we might apply to Gaia or the Earth system stability question, because in Ashby's model, he literally randomly reconnects the components of his machine, and what you have is a series of experiments over time until by chance you rewire your system in a stable configuration in the sense of being dominated by negative feedback, and by definition that means that configuration tends to persist. And that could be an important truth behind why we see an Earth with a preponderance of negative feedbacks and long-term stability. It's a form of selection mechanism, in fact, but not in a population of many, but in a population of one that goes through repeated experiments over time. So W4 Doolittle, who some of you may know, is just writing about the same thing in the context of Gaia as well. Okay. But that wasn't too esoteric.
Jane, and then you, please.
Tim, thank you very much. That was really terrific. I want to focus on oxygen.
Good.
You started off talking about the great oxygenation event, and you partway through said that at least it's conceivable, it's possible that there may be some global anoxic thing maybe down the road.
Yeah.
But I want to focus on the current deoxygenation that's happening now.
Quite right.
And as you well know, that's partly a function of burning of fossil fuels, because warmer water holds less oxygen. It's causing waters to be more stratified. There's less mixing. So we get fewer nutrients, lower productivity. And there's also changes in many of the eastern boundary current systems.
Yep.
That are either expanding existing anoxic zones or making them, or creating new ones. So the question is, how important is that globally? And is this just one additional cut in the death by 1,000 cuts, in addition to critters having to...
Exactly, Jane. And that, all I'm trying to add to that, which is a very good line of observation and argument, and I'm with you, this is a serious issue. The point I would try to make is whatever's driving the start of expanding anoxia, I'm afraid the biosphere is not our friend in this case, in the biogeochemical sense, because we well know that when anoxic waters impinge on sediments, we get preferential recycling of phosphorus that supports more productivity. In fact, as you know, I think, you go to the Baltic Sea today and measure this, and there are several published papers on the fact that the expanding anoxia in the Baltic Sea has caused massive measurable increase in nutrient return from the sediments that's supporting more productivity and more anoxia. In fact, if you know anything about shallow or deep lake ecology, you'll know that that is the fundamental mechanism that propels the switches from oxygenated to anoxic lakes. It's the same core geochemistry and microbiology. So yeah, you're absolutely right to flag that up, and I'm trying to flag it up as well to say, once, whatever your driver is, once you start causing anoxia, I'm afraid this positive feedback comes in and tends to make it worse. And our model was about how, at what point do you tip that thing into runaway. You can think about that as a basin or a lake scale, but you can also think about it at a global ocean scale. And it might be 1,000 years time where you could tip it globally, but that's still pretty nearby. And in the meantime, you'd have caused great chaos at a whole load of smaller scales, and great mass extinction, I would expect, along the way. Yeah.
Thank you. Neil, please.
Thank you for a magnificent and magnificently scary talk.
Yeah. I aim to be scarier than Paul. Is he hiding somewhere? He's like the horseman of the apocalypse usually, but I thought I'd try and steal his thunder today.
I was actually going to ask a version of Jane's question, but let me shift it a bit. Could you talk a little bit about ocean acidification and how it fits into your thinking? Because in terms of the rise of global carbon in the atmosphere, it's not just temperature. How do the tipping points relate to acidification, maybe changes in ocean circulation and so forth in terms of the oceans as a system?
Yeah, so I rudely skipped over that, and yet, as you were saying in your talk, we have good evidence that some of the mass extinctions of the past had an important role of ocean acidification as one of these multiple drivers. I guess the most top-level point, though, that should be coming across is usually it's not one kill mechanism, either in the past or in the present. Usually it's a multifaceted thing, and acidification is one dimension of a changing carbon cycle and climate, and deoxygenation is another. Acidification is a serious issue, particularly for those organisms that make calcareous shells or exoskeletons or whatever you would call the coral reef structure physiologically. And I briefly hinted at reefs and sort of took out the slide on those, but there's definitely a threat to corals that could manifest on quite a large scale, and it's a multi-dimensional threat from acidification, warming, fishing, nutrients, things that Jane covered nicely yesterday. If I was to say which corals are threatened first, it would be actually the deep sea ones, because they're in the coldest waters, and cold waters dissolve more carbon dioxide and acidify the most and the fastest. So they fall below the saturation point for aragonite, of which the corals are made first. Would we even notice that up here at the surface? Well, we might do, because we're starting to do the science of these corals down at hundreds of meters or thousands of meters in the North Atlantic, for example. But we're much more usually excited about the shallow tropical ones, which again are getting hit by multiple factors. And the interesting question there is, do they get hit kind of synchronously? Already we see that sometimes they do, the bleaching events becoming more widespread. Is it a tipping point in the way a dynamical systems thinker would talk about it? That's a little less clear, because our kind of tipping point is where you have self-amplifying processes. And in this case, though it's a disaster for the corals or the calcareous phytoplankton, the dissolution of the coral or the plankton shell is a source of alkalinity to the ocean that helps the ocean buffer and take up more CO2. So ironically, it's a negative feedback on the long time scale in the carbon cycle, but obviously it's a catastrophe for biodiversity. So it becomes a different kind of tipping point. You're asking the question, is there a kind of large scale passing of a physiological threshold that's synchronous? And I think there could be, and we'd all care deeply about that. And it could be from these multi-dimensional drivers.
Thank you. Werner, please.
As far as I know, there is no satisfactory explanation to explain the origin of life. You briefly mentioned the origin of life, but that I realized then that's not your topic.
I chose to studiously avoid it because although I've been to several origin of life conferences and I much enjoy the theoretical musings of those in the field, the great problem there is it science? Because can you really test the predictions of your theory? So I have my thoughts on that, but I prefer to focus on the later. I think it's remarkable, and everyone should remark on how quickly life originates after the Earth becomes what we would call persistently habitable, because that, if it's telling us anything in a Bayesian statistical sense, it's telling us that life evolved quite easily if it really started here. And that in itself is extraordinary. I have
actually two comments. You may be aware of part of it, perhaps. The first is NASA, of course, hopes to find life on exoplanets which have living conditions in principle. And their condition to define life is it must not just be a complex organic molecule, but it must be able to replicate, first of all, and secondly, to evolve in the course of time.
And for it to be detected on an exoplanet, it must be globally plentiful, abundant enough to transform the atmosphere to a state of chemical disequilibrium that you can see with a spectrometer from several light years away. So it has to be a global biosphere.
Now, one question which I carry with me since a number of years, could we assume that life originated not near the surface of the planet, but in the deepness of the Earth's crust, where there is a lot of energy available? And that would be anaerobic life, of course. And then later on, aerobic life became only much later possible by photosynthesis and other things.
So there is a thing called the Deep Hot Biosphere, which some of you hopefully know about. That is life deep in the Earth's crust, as far as we've drilled down, in fact, it's more than a kilometre and a half. But actually the source of free energy in chemical form at those depths to run a chemo-autotrophic metabolism is incredibly small. So these are very, very slowly replicating organisms, although their biomass may collectively be considerable. So kind of deep in the crust is not the obvious place to start life, but near a deep ocean hydrothermal vent is one of the which is an intense source of chemical free energy. That is a good candidate place. Mm-hmm. What's interesting about the Deep Hot Biosphere is it gives a doorway in which life could have arisen before what's called the late heavy bombardment. So after the moon forming event 4.4 billion years ago, there were oceans on the Earth, we know that. Life could conceivably have originated then and then cleverly migrated down into the deeper crust to sit out the later bombardment with rocks from space, which essentially evaporated the ocean and formed all the craters we love on the moon in the late bombardment, and then maybe migrated back up again. Okay. If it had done that, you'd see that in the genetic code of Luca, the last universal common ancestor. You'd expect it to be a hyperthermophile, and there's some signs that it was. So that's a possibility. We're getting a little bit off topic, but in a fun way. I know my message comes across as is he just trying to scare you all. Actually, I'm not. I'd actually like you to take away the miracle of your own very existence on this planet, and it's the debt we all owe to past life. Okay. Because the one thing that really upsets me is when I see the World Bank, valuing natural capital at like 5% of capital, when none of us would be here to talk about any of this were it not for this past biosphere.
Thank you. I think we have now to move to the next presentation.